All right, welcome back. This is problem number 3 in the homework set of DC circuits. So for those clever students that watched the first 2 videos and thought, maybe rightly so, that, oh, I don't have to do all this work because I could just, I could just think about of these formulas here in resistors in parallel, and I can kind of use my intuition to figure out what the answers are. Perhaps that's true, and that's great. But now intuition kind of goes out the door. We can think about what's happening here, but we really have to follow these steps using this method. There's another method called Kirchhoff's laws, which we won't cover at this level. But in this method, what I call the traditional method of just breaking down a circuit, what's called I think we call these complex circuits now. These complex circuits which have both parallel and series resistors. Okay, so these two are in parallel with each other, but they're not parallel to this one. And this one is in series with the combination of these two, but it's not in series with this one and with this one. Okay, you can see it splits right here at this junction. All right, so for those, we're going to have to do this method. You have to do the work. You have to do it. You have to break down the circuit. You can't just think about it and get the right answer. All right, so let's dive in to see how that's done. I've already broken the circuit down, which is the circuit we start with here. I've already broken it down into its component parts. Let's just remind ourselves that this is the positive voltage, so we know that the current coming into the circuit, I'm going to call that IN. I'm going to call this delta VN. The voltage drop across our circuit is VN, IN. That current is going to come through the 150. I'm going to go ahead and relabel it I-150. But just know that I-150 and IN are the same because they're the same current. They don't branch. This current is now going to split. This IN is going to split, and some of it's going to go this way, which I'm going to call I-490. And this one is going to split this way, which I'm going to call I-1000. 1K, of course, is 1000. Now, these two currents are going to reconnect right here. And it's got to be what was the current that comes in. So the current that comes into the circuit is also the current that comes into the battery. Okay, so that's kind of the big idea, and that's what we're going to look for. We're going to look for what is the voltage drop across the 150 ohm resistor. Okay, and that's going to be called delta V150. And what is the voltage drop across the 490? What is the voltage drop across the 1000? And what is the current through each of these? All right, so here's how to do it. We're going to take our circuit, and we see that these two are in parallel, right? So I'm going to break down those two, and I'm not going to show the calculation, but just suffice it to say that the resistance here, the parallel resistance, is 328.9. And if you don't know what I'm talking about, grab your equation sheet and remind yourself that this is the equation that you use to find RP. And notice this left-hand side is 1 over RP, not RP. So we end up getting this, okay? And now we have our original 150, which we just redraw. The only thing I did was compress these two here. And now we're not done because we don't have one resistor. So now we see that these two are in series. Yay! And so now we come down here and we can recalculate this, and we see that we know that the series resistor, this is the easy one, is just the sum of the two resistors. Okay, and so now we get an equivalent resistance down here. So why do we do this? Well, we do this so we can figure out what we don't know. Well, what we do know is delta V across our series resistor is simply delta V of the input, which is 12 volts. Okay, because the voltage drop across this resistor, as you can see, is 12 volts. All right, if we use Ohm's law, delta V is equal to Ri, we can solve for what we don't know. The only thing we don't know is the current, and the current coming through this IN, or you can label it RS if you want to. That IN, that current going in, is this current up here, and that is what we're trying to find. Delta V over R. Now, which delta V is this? It's delta V in. And which R is this? It's RS. It's the voltage drop across a particular resistance. And so we can calculate that. I'm just going to do it out like so. Is 12 volts over 478.9 ohms, which is 0.025 amps. Watch these zeros. We lose these zeros. We write them a lot. We lose them, which is why I often will write this as milliamps 20. Oops, grab your eraser. Make sure the eraser's handy. You're going to need it for these kinds of problems. It's 25 milliamps. Now, we don't really use milliamps in our calculations because we need volts and ohms and to give us amps, but it's nice to have whenever we check, and you'll see that in a second. All right, so now we've learned everything we can about this, so now let's take this information and let's bring it up here. Okay, so what did we just learn? We just learned that the current going through here is 25 milliamps, or 0.025 amps. Okay, and that current has got to be the same through the 150, has got to be the same through the RP, because they don't branch. So let's just apply Ohm's law to each of these resistors. Okay, and so delta V of the 150, the voltage drop, which is the only thing we don't know now, across the 150 ohm resistor is equal to R150 times I, and I150 if you want. And that's going to equal 150 ohms, and the I is 0.025 amps. Okay, and that we end up getting is 3.75 volts. All right, so now we know the voltage drop across our 150 is 3.75. So I'm going to put a box around that because that's one of the answers we need. Okay, I also know that the current going through, our 150, let's just make it really clear, make sure our teacher knows we know what we're doing. Okay, so done. With the 150 ohm resistor is done. We know everything there is to know about it. But let's keep going with the RP. So let's reapply Ohm's law here. Delta V of the parallel resistor is what we don't know, is equal to RP times IP, if you want to call it that. And RP is 328.9 ohms. IP is the same current here. It's 25 milliamps. And when you do that calculation, you get 8.22 volts. Okay. Now that's we're not done there, right? We still have to keep going up and figure out what the 490 and the 1K is. But let's pause here and check as we go. Okay. So the voltage drop across both of these, right, should be Vn, which is 12 volts. Okay. And the voltage drop across two series resistors, they add up. And if you don't remember that, grab your handy sheet, and the voltage drop going into the resistors are equal to their sums. And what's that sum? It's delta V across 150 plus delta V across the parallel resistor. It's that voltage drop plus that voltage drop. Okay, and we hope it's 12 volts because that's what Vn is. We put a little question mark there. Maybe it is, maybe it's not. 150 we said was 3.75 volts. The voltage drop across Vp is 8.22. Does that equal 12 volts? Well, not exactly, but it's good enough for government work. 11.97 volts, it's just a rounding error, is equal to 12 in the world of, high school physics. And we say, yay, we got that part. So we check as we go so that we don't waste our time going up here. If this number does not 12 volts, then whatever we do up here is not going to work. So figure out what your mistake is down here. Maybe you subtracted or added wrong or divided wrong, or you forgot your zero or whatever. Use the check as you go to help you. Okay, so now we're almost done. What did we learn from this down here? Well, we knew the current going through RP, and we know RP. So what did we learn? We learned that the voltage drop across RP is 822. In other words, if I put a dot here and I put a dot here, that's the same as that dot there and the same as that dot there. Okay, we can label it A and B if you want, and there's A and there's B. So that's the same diagram. In other words, the voltage drop between A and B is 8.22. The voltage drop between A and B is 8.22, which means delta V of 490 is 8.22 volts. So that's something else we know. There, we can answer that question. All right, and we also know that delta V across the 1000 is 8.22 volts. We know that as well. Okay, now all that's left to do is figure out what the current is through each one. And we can use Ohm's law again, okay, the generic version of Ohm's law, and then we can write what I is, right, because that's what we're looking for. We're looking for the current. Oh, sorry. Use your eraser. And what current are we looking for? In this case, it's the 490 ohm current, or through the resistor, 490 ohm resistor. And so this is 490, and this is 490. I like to label things to make it, make it unambiguous. So what's the voltage drop? It's 8.22. And the resistance, of course, is 490 ohms. And when you calculate this, you end up with 0.0168 amps. That's a 0, which is, again, just for comparison purposes, 16.8 milliamps. Okay, and so there is I490, and there's our answer. There. We do the same here for the 1000. I can just reuse this equation. The voltage drop is 8.22. It's parallel, right? Over 1,000 ohms. Hopefully that math is easy for you. And we'll get 0.00822 amps, which is equal to 8.22 milliamps. And that's our I1000. And so there is our answer for that. So we've answered everything. We know the voltage drop across each resistor. We know the current through each resistor. All right. But before we leave this, let's just make one last check. How can we check this? Well, we know that in a parallel resistor, or a circuit rather, right? Because this last little bit was parallel. We're just going to focus just on the parallel part. The last little bit, we know that the current, in parallel, we know that the current going into the parallel circuit is equal to the sum of their currents, okay? And so let's just do that check. I'm going to do the check down here. Sorry, I'm running out of room. Okay. The final check, we know that I going into the parallel, IP, is equal to I490 plus I1000. So let's see if that's true. So the I490 is 16.8. Again, I'm checking with milliamps just so that's easier for me. And the I1000 here is 8.22 milliamps. And when you add those up, you get 25.02 milliamps. Is that what we were looking for? remember the current going into this junction here, the current flowing into the parallel circuit was this current here, which was 25 milliamps. And that, oh, sorry, the current going in was 25 milliamps. So that's close enough for us, right? And we say, yay, and we know that we get it right. So physics is great because you can walk out of the test knowing you got it right, but it's also terrible. You can walk out of the test knowing you got it wrong, but at least you can go back and try to find your mistake. Again, check as you go. It doesn't make sense. Is your resistor less than 1 ohm? If it's less than 1 ohm, it's probably wrong, right? Resistances in this world of physics are usually bigger than 1 ohm, although not always. But well, on my test, they always are. All right, one more problem to go. The fourth problem, which is the hardest problem, but it's basically the same step. We break down the circuit into its smallest and smallest components into equivalent resistance, and then we recalculate as we go back up. So the fourth problem is we just add another resistor basically to the circuit, and we'll see what that looks like. Thanks for watching, and I hope this was helpful.